It's my great pleasure to welcome you all to this first session of the afternoon, focusing on the science, and that is the terrestrial perspectives session. So the aim of this next hour is going to be to kind of look towards Earth and discern from it those key aspects of our planet that inform our search for life in the universe, both at a molecular, planetary, and astrophysical scale. Just to introduce myself briefly, I'm Ollie Shorttle. I've got a joint position, assistant professor between the Institute of Astronomy and Department of Earth Sciences. And it's a position, the remit of which could perhaps be seen to be to provide a terrestrial perspective to exoplanetary sciences, and in turn maybe translate some of the fantastic discoveries of exoplanetary sciences back towards Earth and our own perspective on Earth as a planet in the universe. I want to, before we start with three fantastic panelists, I want to introduce this session with really 4 spectacular images of Earth, which provide some perspective on the key aspects of our planet which have contributed to its habitability, and from which we may gain insight into the requirements for habitability of planets throughout the galaxy. The first thing we learn from Earth as a key requirement for life is water. And this is sort of evident even from this grainy image, one of the first images captured of Earth as a planet floating in space in 1966 from the Molniya 1 satellite. And even in this grainy, low resolution and black and white image, the contrast we can see across this gibbous disk of the Earth here is defined by liquid water, primarily the dark patches, the oceans, and the light patches, the clouds. Of course, a few years later, going to 1972, and this image, this famous blue marble image from Apollo 17, we see spectacularly the continents, oceans, and clouds of the Earth. And everything we're looking at in this image is either water, the oceans, the tropospheric clouds, or the giant South Polar ice cap, or has been shaped by water, the continents and their present-day elevation and shape, or indeed even their very existence can be attributed to the presence of water on Earth. And water really operates across all scales in our planet. It's essential for all life. And we can see this in this image, a microscopic image of Pachyrocloccus cyanobacteria. These bacteria use water with CO2 and use sunlight to photosynthesize, producing oxygen as a byproduct of the production of sugars. And these cyanobacteria, they live in water, they utilize water in these chemical reactions to produce energy, and in so doing have transformed the atmosphere of our planet to one which is rich in oxygen, and which all life on Earth today, or much of life on Earth today, utilizes for its energy. These cyanobacteria, some of the earliest known oxygenic photosynthesizers, and ushered in the rise of oxygen to Earth's atmosphere about 2.5 billion years ago, proliferating in the world's oceans. Kind of going on to the other end of the scale, water is also key for regulating our planet's climate by controlling the amount of greenhouse gases in the atmosphere. Here we're looking at a stunning image taken from the International Space Station, looking south across the Tibetan Plateau towards the Himalayas, with Everest in the center of the image. And we're seeing the deeply incised valleys of this mountain range have all been sculpted by the action of water, both as rain and ice carving out and grinding down rock. And this process is not only a mechanical process transporting this rock ultimately to the Ganges floodplain, but is also a chemical one in which water enables the reaction between the carbon dioxide in Earth's atmosphere and this ground-up rock to ultimately draw the carbon dioxide out of the atmosphere and precipitate it as limestone, thus closing the geological carbon cycle and regulating the amount of carbon dioxide in Earth's atmosphere. And this simple reaction has, in all likelihood, stabilized Earth's climate over its entire 4.5 billion year history, controlling the temperature at Earth's surface against major changes in the luminosity of our sun. And it'll be the same reaction which over the next 10 million years, in the absence of any intervention from us, draws anthropogenic CO2 back out of the atmosphere. It's also the presumptive reaction which regulates climate on rocky planets throughout the galaxy. So it's a really kind of key piece of our understanding of how planets operate. And it's made possible by the presence of liquid water. The second lesson from looking at the Earth is the importance of interior atmosphere connections. And now we move further away from the Earth, 27,000 kilometers in our first images, now to 380,000 kilometers, looking back at Earth from across the limb of the moon towards Earth rising above it. This is an image taken from the crew of Apollo 8. And what we see here in the foreground are the lunar highlands. And this landscape, this rugged landscape on the moon, records an epoch in Earth history which is lost on Earth itself. And that is of the birth of our planet as a roiling ball of magma. And this epoch in Earth's life, when perhaps it looked more like this, is a really key one for redistributing life-essential elements around the planet, both metals to the center of the planet and gases such as nitrogen, hydrogen, to the surface, and carbon to the surface, forming the first atmosphere of the planet. And in all likelihood, this would have been the atmosphere in which life emerged via prebiotic chemistry. And these connections between the interior of planets and their exteriors continue today and are essential for the maintenance of life and the environment. And most dramatically, these connections are maintained by eruptions such as this, the spectacular 1980 Mount St. Helens eruption, during which huge quantities of sulfur, water, and carbon dioxide were injected into Earth's atmosphere. And these eruptions form a key part of the geological cycles, returning to the atmosphere those very essential elements which also are drawn from it by the kind of processes we've already discussed. The next thing we learn as being key in building a habitable planet is what it's made from, its so-called building blocks. And now we're moving to an image of Earth taken 1.5 billion kilometers away, looking towards the night side of Saturn in this remarkable image from the NASA's Cassini probe. And Earth and the moon hang below the rings of Saturn as this pale dot here. And from this vantage point now in the outer solar system, beyond the orbit of Jupiter, we see something really striking, which is that planets are made of different stuff than the planets we see adjacent to it, Mars, Venus, and Earth itself. So whereas we look towards Earth and we see essentially a ball of rock with a delicate veneer of gas, of carbon dioxide, nitrogen, and water, we see in Saturn a planet enveloped in a thick layer of hydrogen and helium, a vastly different and alien world to Earth and the inner solar system planets. And this thick layer of hydrogen and helium means, for example, there's no clear surface, no clearly defined surface on the planet, like we stand on today and which much of life on Earth exists on, making this planet likely relatively inhospitable. And you might say that this is just because we're looking at a massive planet 100 times the mass of Earth. And in all likelihood, its mass did fundamentally change the way in which Saturn grew compared to Earth, accumulating vastly more of these gases, these atmophile elements like water, hydrogen, than Earth was able to do. But even looking at the small objects at this distance from the Sun, Saturn's moon Enceladus, for example, which we see here in another image from Cassini, we see objects which are enveloped in vastly more of these atmosphere-loving gases than on Earth. Here, obviously, cold at these distances from the Sun, we see the water present as these giant ice sheets covering the surface of Enceladus. And it's a young surface. We see relatively few craters, and in place of craters, we have giant crevasses, evidencing the tectonic activity that moves the surface of this little moon around. And indeed, as Cassini was flying past, it saw plumes of water erupting from Enceladus, evidencing that beneath this thick icy cap is a vast ocean of water. So this points to the importance of building blocks in the sense that Earth has these life-essential elements, but equally, if Earth had been born slightly further from the Sun, it may well have ended up with vastly too many of them, creating a planet which is distinctly uninhabitable in the sense that we know it on Earth, and perhaps rendering it lifeless. So we've seen three really remarkable images that tell us something about maybe key requirements for habitability. And the fourth image, and the one I want to end on, is this famous image, the pale blue dot image, taken by the Voyager 1 spacecraft as it was on its way out of the solar system, 6 billion kilometers from the Sun. It turned and looked back towards Earth. And Earth here is this dot, less than a fraction of a single pixel in this scattered ray of light from the telescope's optics. And what this image really reminds me of is that as far as our explorations reach away from Earth into the solar system and beyond into the galaxy, we're always going to be looking back towards Earth to recontextualize its position and our understanding of it in the universe in light of our discoveries, but also to guide our next steps forward. Our speakers are going to gradually bring us back from the edge of the solar system to focus in on Earth. And we're going to be starting with Mark Wyatt, who'll be giving the first talk on delivery of elements to growing planets.